Data storage using HDFS. Executives at a startup IT company had been struggling with big data workloads and large data files. The data explosion was putting huge pressure on business to seek for innovative solutions to address the big data challenges. The business needed more capable, faster, powerful, and cost-effective computing resources, including servers, networking, and storage infrastructure. Achieving proper balance of compute power, data store, and network was critical to optimal performance. As a result, the company decided on a series of steps to address the challenges of handling with the volume and speed of big data. The first step in this direction was to migrate from their traditional tower model servers and adopt a more robust and cost-effective rack model of servers. The rack servers offer increased computing power and improved reliability at reduced cost. Each server unit is referred to as a node. Several nodes, depending on business requirement, are connected with optic fibers to form a cluster. Rack servers are ideal for virtualization and cloud computing. That is, they can be easily scaled up by adding more nodes to the system as per business requirement. There is also provision for replacing older, slower node with new nodes with better performance. Next, the business executives decided to adopt Hadoop Distributed File System, or HDFS, which is a part of the Apache Software Foundation project. This approach will provide a fault-tolerant file system that can run on commodity hardware, as well as one that allowed for the reliable storage and processing of large amounts of data at a low cost. We know that HDFS is a data storage cluster that facilitates the storage and management of related files across machines. It offers several unique capabilities and benefits. These include it stores data reliably. It writes data only once and allows data to be read from any cached copy of files replicated on different machines. This removes the need to verify whether the data contents have been modified. It is fault-tolerant. It detects faults quickly and applies automatic recovery. It ensures portability of data and processes across heterogeneous commodity hardware and operating systems. Along with scalability, it allows for reliable storage and processing of large amounts of data, as well as economy by distributing data and processing across clusters of commodity personal computers. It offers reliability by automatically maintaining multiple copies of data. All these facilities together make HDFS the perfect solution to handle big data. In this video, we will discuss the Hadoop HDFS and learn the process of storing files in HDFS. Let us first discuss about the architecture of HDFS and how it contributes to the storage and processing of data in HDFS. HDFS comprises of interconnected clusters of nodes where files and directories reside. It follows a master-slave architecture. HDFS cluster includes a single NameNode master server and multiple data nodes that run on the HDFS cluster. The NameNode manages the file system namespace and regulates client access to files. Data nodes store data as blocks within files. These blocks are distributed among the data nodes in the HDFS cluster and are managed by the NameNode. That is, the NameNode keeps track of where data is physically stored in a data node. But how does HDFS keep track of all these pieces? The short answer is file system metadata, or data about data. HDFS metadata can be thought of as a template for providing a detailed description on when the file was created, accessed, modified, deleted, and so on, where the blocks of the file are stored in the cluster and who has the rights to view or modify the file. It also provides details on how many files and data nodes are on the cluster and where the transaction log for the cluster is located. HDFS metadata is stored in the NameNode server, which is a repository of all the HDFS metadata and data nodes. Data nodes refer to the place where the user data is stored as blocks within files. The name node is therefore critical and is always stored in the memory, and data notes are stored in racks. Racks are physical collections of nodes in a single location. Now that you have been introduced to name nodes and data nodes, let us understand their roles as part of the HDFS architecture. Each cluster in HDFS has one master name node and many slave data nodes. The existence of a single name node in a cluster simplifies the architecture of the system because it acts as a single arbitrator and repository for all HDFS metadata. As a result of the relatively low amount of metadata per file, the name node stores all of the metadata in the main memory, enabling a fast random access. NameNode also manages all the file operations such as read, write, create, delete, and replicate data locks on the data nodes. It also manages the file system namespace, which is a collection of files in the cluster. So how exactly do name nodes work? The name node is vital to the correct operation of the cluster. Hence, to ensure the availability of data, a secondary name node is also available. Though a relationship exists between the name node and the data nodes, they are loosely coupled. This allows the cluster elements to add or subtract servers as the demand changes. Normally, one name node and possibly a data node run on one physical server in the rack, while other servers run data nodes only. Within the HDFS cluster, all the data nodes are collected into a rack. The name node uses a rack ID to keep track of all the data nodes in the cluster. The name node tracks the data on various data nodes that make up a complete file. Now, let us understand how do data nodes work within the HDFS architecture. We know that in HDFS, data is stored in multiple data nodes. Consequently, access to a file will require access to multiple data nodes. Data nodes benefit throughput in two ways. For one, the data node stores each HDFS data block in a separate file on its local file system, with no knowledge about the HDFS files themselves. In addition, the data node does not create all files in the same directory of the native operating system, and instead determines the optimal number of files per directory and creates subdirectories appropriately. But how does DataNode and NameNode interact? Data nodes constantly interact with the NameNode to check if there is anything for them to do, which alerts the NameNode about the availability of data nodes. Data nodes also communicate among themselves to cooperate during normal file system operations, which is important, as blocks for one file are likely to be stored on multiple data nodes. Data nodes work by providing heartbeat messages to detect and ensure connectivity between the name node and themselves. When a heartbeat is no longer detected, the name node unmaps the data node from the cluster and keeps on operating as though nothing has happened. Then, when the heartbeat returns or a new heartbeat appears, it is added to the cluster. Data nodes that we have just discussed are stored in racks. Racks are physical collections in a single location. Using the Hadoop rack awareness process, the name node determines the rack ID that each data node belongs to. Rack awareness also is an important characteristic of the data storage in HDFS. Large HDFS instances run on a cluster of computers that is usually spread across many racks. Network bandwidth and performance is usually better between machines in the same rack than between machines in different racks. A simple policy is to place replicas on unique racks, which not only prevents losing data when an entire rack is lost, but also evenly distributes replicas in the cluster. In addition, it also allows using bandwidth from multiple racks when reading data. An optimization of a rack-aware policy is to use a number of racks that is less than the number of replicas. To minimize global bandwidth consumption and read latency, HDFS tries to satisfy a read request from a replica that is closest to the reader. This means that a replica is used to satisfy the read request if it exists on the same rack as the reader node. Now that we know the architecture of HDFS, let us now discuss how data is actually stored and processed in HDFS. To understand how HDFS works, think of a file that contains all the volumes of an encyclopedia, with Volume 1 being stored on Server 1, Volume 2 on Server 2, and so on. If we were to equate this with the Hadoop world, pieces of this encyclopedia would be stored across the cluster, which is a larger unit that is used to organize and identify files on a disk. Then, to reconstruct the entire encyclopedia, your program would need blocks from every server in the cluster. To achieve availability, if components fail, HDFS replicates these smaller pieces onto 2 additional servers by default. This redundancy offers multiple benefits, the most obvious being higher availability. Therefore, HDFS is so resilient that these blocks are replicated throughout the cluster in case of a server failure. Let us now see how this is translated to data storage in HDFS. Now, we know that HDFS is implemented as a block-structured file system in which individual files are broken into blocks of a fixed size, and these are stored across clusters. Each data file is broken into equal-sized blocks of 640 MB, and each block is then stored in 3 different data nodes. This unique capability offers fault-tolerant and faster processing capabilities. But how is this done? The process of storing each block in replicates of 3 ensures data availability even if any one of the nodes becomes non-functional, and thereby enhancing the fault tolerance capabilities. The splitting of the file in equal-sized blocks also ensures that all nodes perform at the same speed and efficiency. As beneficial as the HDFS file organization is, there is a downside. Because several data nodes are involved in the serving of a file can become unavailable if any one of the machines is lost. To avoid this problem, HDFS replicates each block across 3 machines by default. So, when a client is writing data to an HDFS file, this data is first written to a local file. Then, when the local file accumulates a full block of data, the client consults the NameNode to get a list of data nodes that are assigned to host replicas of that block. After that, the client writes the data block from its local storage to the first data node, which stores the received blocks in a local file system, and forwards that portion of data to the next data node in the list. This is repeated by the next receiving data node until the last node in the replica set receives data, which stores data locally without sending it any further. Let us now look at a few special features of HDFS. 2 important features of HDFS are data replication and resilience, allowing client applications not to have to track the location of all the blocks. In addition, HDFS supports the capability to create data pipelines, which is an important feature of Hadoop MapReduce. A 4th feature is the existence of a rebalancer service that balances the data nodes on the basis of how full each set of local disks might be. The rebalancer runs while the cluster is active and can be throttled to avoid congestion of network traffic. Let's evaluate your understanding of how data is stored in HDFS. HDFS works by breaking large files into smaller pieces, called blocks, that are distributed among the data nodes in the HDFS cluster. Let's do a quick recap of what you've learned in this session. HDFS is a reliable, high-bandwidth, low-cost data storage cluster that facilitates the management of related files across machines. HDFS is implemented as a block-structured file system that follows a master-slave architecture. An HDFS cluster includes a single NameNode master server and multiple data nodes that run on the HDFS cluster. The NameNode manages the file system namespace and regulates client access to files. Data nodes provide heartbeat messages to detect and ensure connectivity between the NameNode and the data nodes. Using the Hadoop rack awareness process, data loss is prevented when an entire rack is lost, and replicas are evenly distributed in the HDFS cluster. HDFS replicates each block across 3 machines to prevent a file from becoming unavailable if any one of the machines is lost.